Hello everyone. In this video, we are going to talk about model reduction. So as you know, when you are designing a controller for any system, whether it's given by state space or equations or transfer function or anything, one of the factors that determines the simplicity or the difficulty of designing the controller is order of the system. So if you have a first order or second order system, there are very well established formulas and techniques for basically analyzing the stability of the systems and designing compensators, controllers, and so on. But if you have a system with 40 something, 50 something, 100 states and or order of polynomial in the numerator and denominator of transfer function, that is a lot harder to analyze and to design a controller for. So my goal here is to tell you how you can potentially reduce the order of a system that has a very high order by this application in MATLAB called model reducer. And then we have to go behind the scene and see how this model reducer is actually reducing the order of the system. And the technique for that is using Hankle singular values that I mentioned in one of my previous videos. And those singular values are based on some new topic that I have not talked about, and those are called Controllability and Observability Gramians. So I need to give you some application, which is model reduction in MATLAB, but also go in theory of control behind the scene to explain that. Now, there is another way for model reduction, and that is closeness of poles and zeros, and I'll show you that one as well. Now, to demonstrate what I'm talking about, here I have imported this model called data. So this data.mat has a model of a system that has an order of 48. So if you look at here, you can see that when I read this in and I get the A, B, C, and D matrix from the G model that is in this mat file, and it's the state space model, I get the numerator and denominator of that using SS to TF command and then pass it to the TF to get the transfer function. And if you look at my transfer function, look, there is a 47th order in the numerator and there is a 48th order in the denominator. Okay, so my transfer function is huge, right? And the same goes for matrices, like matrix A is 48 by 48. So the question is this big order really necessary? Can I simplify the system? For that, we're going to load the model reducer app, which you can get from the apps, or you can directly run it from the command window. So here we are going to run the model reducer app. Let's go ahead and bring it up. We import our system into it, and then it allows us to visualize the poles and zeros of the system, the Hankle singular values of the system, and then we can see if we reduce the system order from 48 to something smaller, how close is the response of the reduced order system to the original system? Is it acceptable or not? So this is that application. Now we go and import our model. And you can import it either from a transfer function version or from a state space model, doesn't matter. So here I go ahead and import the transfer function model. And soon I can go to my plots. And it also allows me to basically create a model reducer. So you wait a second, it brings up all the plots, and then we're going to go from there. You see here, it is importing it, and if you just click on it, there we go. So now we are ready to start. You see, that is my transfer function. And now I can get the plots of the system. So I can, for instance, look at the pole zero map, right? So if I click here, it shows me the pole zeros of this original system with 48 states. Let's take a look at that, see what we can find out. There we go. So let's look. if you look here and zoom into any area, you see there are a bunch of places that there are poles and zeros that are almost on the top of each other, almost canceling each other. Look at here. You see, I mean, here it's a little bit different, right? Very close though. But if I go back, some of these other ones, they're extremely close to each other, right? So it's not really the let me do it one more time. Seems like I zoomed in too much. Here we go. So there are a bunch of poles and zeros that are very close, and I might be able to simplify some of them. Okay, so this is an indication that you have a bunch of weak dynamics in the system represented by close poles and zeros, which kind of could be canceled. So if I want from here, I can decide which ones to get rid of, right? Or, as I said, there is the other method. So if I go back to model reducer, now I can go here to this method called pole zero simplification, or I can go to this method called balance truncation. So let me show you. If I go to pole zero simplification, it allows me to manually remove some poles and zeros and simplify the system, okay? And then I can export that simplified system into the workspace. I can look at the behavior of that, and I can see some of that behavior also here under plots. So look here. Here right now, it is suggesting me something. It says, hey, if I bring the system order to 30 from 48, for instance, if you look at the Bode plot, magnitude and phase, this is the Bode plot. The red one is the reduced system. The blue one is the original system. Okay, and you see that they are mostly on the top of each other, except for this mid region. So if your system is not working in this region, maybe you don't care about it because the rest of it, the magnitude is almost the same. The phase, there is a phase difference though, and that phase difference starts from this point onward. So I can say probably if my system is working within like 1 hertz to something like here, which is about 25 hertz or 24 hertz or something, if my system is only working in this region, guess what? My 30 state system and 48, they are doing almost the same. Or if I don't care about the phase much, all I care about is the magnitude, then guess what? Literally for all of the region up to 1000 hertz or more, except for the region somewhere between like 23, and it's, by the way, I said hertz, I correct myself, radians per second. Everything here is radians per second, not hertz. From 23 radians per second to somewhere like, let's see, it's about 60. So if I'm not working in that range, 23 to 60, 61 radians per second, and phase is not critical to me, magnitude is, guess what? That's a very good one. And there is this control here that you can have, and this one will allow you to basically have a tolerance for how close the poles and zeros could be before they can be eliminated. So if I, right now is 10 to the negative 5. Now if I say I want them to be up to 10 to the negative 8, now you have to keep more poles and zeros because they have to be very close now for them to be eliminated. So now the order is 32 instead of 30. You have to keep more poles and zeros, at least 2 more. And the thing is, look here, the behavior of this system with order 32 is almost the same as the one with order 48. So clearly you see that 16 of the poles can literally be eliminated by 16 of the zeros, which you can see here. That's one of them, because the poles and zeros of the red and blue system are again the new and the old one, and you can see that these two are too close. These two, they are too close to each other. We can get rid of them. This part we have to keep. These parts we have to shift a little bit and keep, but some of them are literally not useful. Now, if you are allowing for more variation in the system and you say, well, even if they are not super close, still get rid of them, then you move this slider to the right. So you allow more deviation and still getting rid of it. Let's see what happens. Now we go down to order 28. Now, of course, you see a little bit bigger difference here. You can even go further down and reduce the states further. Okay, now sometimes it does a little bit unpredictable thing. Let me go all the way to the right. Yeah, ideally it should go down, but sometimes you see it's not, and that's why I don't personally use this pole zero closeness. You can do it if you want. That's not my preference. I use the Hankle singular values. That's quite a bit better. But you see that basically I can pick any threshold I want. I can see what I want to do, and I can decide which poles and zeros I don't want. Now here, you see, these are those locations of the poles and zeros, right? And the ones that you can basically have or not have depending on the value of this slider. And the comparison plot here is model response. You can look at the absolute error between them or relative error. And once you feel like, hey, this is what I want, correct? Then you can go and say, save the reduced model. Now it is going to save it to the data browser, not to the workspace. We'll see. So when I say save, it is going to export it here, not to the workspace, but I'll show you how to export it to the workspace. So this is something like this. Now, as I said, another way you can do it is this one, balanced truncation. This is using this notion called Hankle singular values. What is this? Let me show you. So here you get this plot, and here these are the states of the system, and of course I have to do it for the original one. So let me do it for the original one. Okay, because right now it is doing it for the reduced one. I want to do it for the original one. There we go. So for all of these states, for each one of them, it is showing a state contribution or a Hankle singular value. And right now, for instance, it is suggesting me that I keep only these first 14 states and go down to order 14. If I do, then the system, original system with 48, the response of its body plot is blue, and the one with 14 states is the red one. And you see, actually, they are relatively close. I mean, except for this few peaks that you miss and this region here that the phase is a little bit messed up, almost up to 100, 110 radians per second, you are doing really great. And I can go from 48 to 14 because I here manually pick the states that contribute the most to the system dynamics. What does that mean? I'll tell you. But I literally pick the ones that I want. And MATLAB, by default, it is suggesting something to me. It says, hey, this is good. But if you don't like it, well, say, no, I don't want that. I want to keep more states. Maybe I want to keep 20. So click here and put it to 20. And look at here. You're almost like identical. So I can easily keep this system with this 20 states, and it performs almost identical to the system with 48 states, right? And that's all I need. I can say, okay, save this for me here. And now that I got these two good models, especially this one that is really good, I can simply right click on it and say, hey, export it for me to the workspace. And it will. And also export that 30 as well for me. Export. So now if you go to your workspace, there we go. Look, this is that 20, and this is what? This is the 30. So both of these models are there, right? And they are in the form of state space as well. And I can look at the behavior of these systems. Do you see? So this is really a powerful method, and I can go to the plots now, right? I can look at any plot that I want. So it shows the body plot, but for instance, if I want to look at the step plot, I can also look at the step plot. Okay, so here is the step plot of the system with 20 states. And let's see. So this is the one with 20 states. This is the one with 48 states. Look at them. They are identical, right? Almost identical. And you can even get in the step response, you can get peak response, rise time, settling time, transient time, and so on. Okay, so you can easily see all of those properties here, right? You can change all of these, but you clearly can see that. Look at these two. Except for some small shift, they are very, very close to each other. Now you might say, I want to put both of those graphs in one single axis so I can see them side by side, not switch between this plot and that. Can I do it? Yes. So you pick the original one, hold down Control, pick this new one, and now do the step plot. There we go. Look, very, very similar responses, right? I got very, very similar step responses out of these two. Or I want to see, for instance, an impulse response of the two. Let's create that. There we go. You see, their impulse responses are very similar. I want to see their Nyquist plot. I can create Nyquist plot for the two and so on. Okay, so the goal is to create any kind of plot that you want, right? And see whether they are up to your expectations or not. If they are like this, guess what? I'm doing a good job. I can easily replace my system with order 48 by my system that is order 40. Okay, so this is your model reducer app, which is very, very powerful. And you can see that if I go to this GT, right, and then reduced 20, this one, you see that, look, my A matrix is basically 20 by 20. My B is 20 by 1, C is 1 by 20, and D is basically 1 by 1, right? So you see, I reduced the order big time. While if I went for G, they were 48 by 48, correct? So you can see that here. So now what's happening behind the scene? The pole zero closeness was kind of obvious. If they are too close, you might consider eliminating them. But what about these Hankle singular values? This needs a little bit deeper theory. So here I need to explain something for you. Yeah, first I was talking to myself, should I do that? And then say, yeah, you opened the can of worm, you better explain it. So if I have a linear time invariant system with these equations in the state space, first, I need to define two things for you that are new. One is called the Controllability Gramian. The other one is called the Observability Gramian. And these are different from Controllability Matrix and Observability Matrix, okay? They are different things. If you watch my videos, you know that under the same playlist, I talked about controllability and observability matrices, right? It's this video here. Okay, and this matrix here that you can see B, AB all the way to AN minus 1B, that's called the controllability matrix. The system is controllable, which means from my inputs, I can control any of my states to go from any number to any other number or any value to any other value. I can do it for all of them if this guy is full rank. And then observability, which was CA all the way to CAN minus 1. This was called the observability matrix. And again, if this one is full rank, the system is fully observable, means by watching my output over some time, I can estimate my state at some point, at some initial point, okay? And I can do it for all states. So if you want to know the meaning of controllability and observability for a system in state space, this is it. But this is different. This that we are talking about is Gramian. Gramian is a little bit different. What is that? So the controllability Gramian matrix W of C tells us how much energy it takes to move the system from origin to a desired state using the inputs. Remember, the controllability itself means I'm able to move, let's say this is the state space of a 2DOF system, right? Or 1DOF system like a mass spring system. So for instance, this is X dot, this is X, right? And let's say I start at origin and I want to go to this location here. So if I want to move in that direction, can I do it? Or if I want to go from here to here, can I do it? Or from here to here, can I do it? If that controllability matrix was full rank, yes, I can go from any state to any other state in the state space by applying sufficient input. Okay, but here we are talking about, yes, I can do it, but how much energy does it take to do it? How easy it is to go from 0 position velocity to, for instance, a non-zero position and some maybe zero or non-zero velocity, right? How easy it is to reach a state. How much energy should you basically put into it? How much energy should you spend? This is controllability Gramian. Now, first of all, how do we calculate this, right? That's the first thing. How do we calculate this and how do we interpret this? We can show that the controllability Gramian can come from this integral from 0 to t of this one, the state transition matrix, times BB transpose that one dt. So if we can calculate this, that is the solution. The solution is the Gramian controllability. Or if we solve this Lyapunov equation, this guy here. If I can solve this Lyapunov equation, because I know A and B, if I can solve this for W of C, then W of C is my Gramian, okay? Now, where does that come from? I'm going to show you. But one thing we have to pay attention to is this matrix that we find is always going to be an n by n symmetric matrix, and it's going to be positive definite. So if I multiply it by any arbitrary vector like x, the result is always bigger than or equal 0 for non-zero x. Now, if my system is fully controllable, WC is actually going to be positive definite, not positive semi-definite. So in this case, I'm going to get this. Bigger than 0. Okay? In general, it's bigger than or equal, but if my system is fully controllable, then it's absolutely positive definite matrix. So that's the relation between the controllability matrix and the controllability Gramian. If that controllability matrix that I just showed you in this video, right, that B, A, B, all of that, if that is full rank, like rank n for a system of order n, then that means the corresponding WC is positive definite matrix. Now, how do we get to any of these formulas, either one or two, right? So the way that you can formulate it is this. You say in this system that I want to start from origin. Remember, in the definition of that, we say how energy it takes to start from origin and go to state. So my initial condition is origin. And then I want to move at time t, which is the horizon. I want to move to some state x of t. Well, if I integrate both sides of this, with respect to x and solve for x, this is a first order ODE in terms of the state vector, then x at time t is going to be the integral from 0 to t of this one, the state transition matrix, convoluted by BU, correct? That's a convolution. And then, so this is, I put the energy in U in the input of the system, and that allows me to go from origin to this state. Now, what's my goal here? As I said, the goal is to minimize the energy. So how much energy do I need for the system? What we call it the control effort. So the control effort is the magnitude of U, or U transpose U, over that entire time. This is the energy you need through input to put into the system to go to x of t. Good? So now what's the goal? The goal is to see which states are easiest to go to, which states are hardest to go to by forming this matrix. So my goal is, let's minimize the energy I need. So this is the function that I want to minimize, subjected to the constraint in equation 3. Subjected to that, the relation between my goal state and my inputs are defined by equation 3. Okay? So I have an equality constraint and I have a function to minimize. And as you know, when I want to minimize any function, or functional in this case, subjected to an equality constraint, I use Lagrangian multipliers, and that is exactly what I'm doing here. So this is my function. These are the two sides subtracted. Ideally, this should be 0 for perfect case, but not necessarily if you don't get to the perfect minimum, right? And then multiplied by the Lagrangian multiplier. So this is my constraint, this is my function. Added together, I get this kind of augmented function. And now all I need is to take partial of this Lagrangian with respect to the input U, set it to 0. If I do that and do some algebra, if you want, you can do the rest of the algebra. I don't want to do all of the algebra here. You can find that the signal U that minimizes my energy is going to be this, and the minimum energy I need is going to be this. Okay? So what has appeared in these equations? In these equations, what has appeared is the inverse of this matrix. Okay? And you might say, where is that? Do I see this integral in here? No, you don't. If you do the algebra, here, the solutions that you will find are not going to be this clean. In these solutions, you will have the inverse of an integral in this place. And then you would call that integral that you have, you would call that integral, this guy, you would call it this matrix W of C, so you can say that is WC inverse. Okay, so the WC that you see, that's that integral that I specified for you up there, right? A to the AT, right? B transpose E to the A transpose T, dt. So that integral appears in the solutions, but you give it a name and call it the Gramian. Good. So again, I leave the rest of the algebra to you because my goal here is to explain the topic, not do all of the algebra. But I told you about the formulation of this problem, and I clarified a little bit of that for you. So let's say fine, we got to these results. And this W of C is exactly this guy that I just showed you. Fine, now what? Now what can I do with this result? How can I interpret that, right? So far we got to this, which is very important, and we got to these two, which are very important. How can I interpret this? This is the time you interpret it. So you know that this WC is a matrix, right? And any matrix has some eigenvalues and eigenvectors, right? Some of the values are larger, some of the eigenvalues are smaller, correct? And by the way, if I call this any matrix A, for instance, you know this quadratic form, this is what we call a quadratic form, X transpose AX. This takes you from the X space to the E space, right? So if this is the X space, the state space, and this is the energy space, it converts a circle to an ellipse for you. And this ellipse has a semi-minor diameter and a semi-major diameter. And these guys correspond to the lambda. So lambda min and lambda max of what? Of the A matrix. Because this is what you did. Okay? So now this is the energy space. If you want to have the minimum energy, what do you need? If you want to have minimum energy for any direction, you have to have the minimum eigenvalue of this A matrix. But in this case, that A matrix for you is the WC inverse, right? So the minimum eigenvalue of WC inverse corresponds to the maximum eigenvalue of the WC itself, because you know that a matrix and its inverse, their eigenvalues are kind of opposite of each other, right? If WC in a direction has minimum eigenvalue, the WC inverse has a maximum eigenvalue in that direction, and so on. So what can we conclude? We can say that if the WC matrix, the Gramian matrix, we can say that in the direction of large eigenvalues of the Gramian, then the eigenvalues of the inverse are small, so these are the directions that are the minimum energy for them are used to take there. So the directions corresponding to the biggest eigenvalues of WC. And what are those directions? You're right. The directions corresponding to any eigenvalue is called the eigenvector, right? So here, this one, which is WC inverse, I want the minimum of that. So for the WC itself, that corresponds to this maximum direction of that. And this direction for it, this direction is the eigenvector corresponding to the maximum eigenvalue. So if I want, in my original system, if I want to go from this origin to this direction, in this direction, it is going to take minimum energy from me to get there. If I want to go in this direction, it is going to take maximum energy for me to get there. And anywhere in between is kind of between this min and max energy. Okay, so this is the idea of the controllability Gramian, how much energy you need to go from origin to any desired state. Those are determined by the direction of eigenvectors of WC, and the energies are determined by eigenvalues of that. Good? This is the observability Gramian. Now, there is another thing called, controllability Gramian. Now, there is another thing called observability Gramian. What is this one? Similar to the controllability one, this observability one will tell us how well we can infer any internal state by measuring the output. Remember, observability itself is, the observability matrix is whether we can even infer the state from the measurement or not. But this one is about how well we can do it, how easy it is to infer a state by measuring the output. Okay? So it's about the quality of it. It's not just about doing it or not. The same for controllability Gramian. We know we might be able to control a state, but how easy it is to do that, how much energy it takes. So a similar thing here, right? How much measurement do we need to have to be able to infer an internal state? That is, again, determined by observability Gramian, W of O, and similar to W of C, that was the solution to this Lyapunov equation. The W of O is also the solution to another Lyapunov equation, very similar. This time you need A and C matrices, which are given to you. So this one says, if in a direction in the state space you have low observability, then it is hard to detect movement along that direction from the states. Okay, it is very hard to detect the state by measuring the outputs. So again, we can look at the eigenvalues and eigenvectors of this matrix to see in which directions it's very hard to infer the states from measuring output and in which states it's the easiest. Good? So fine. We have these two. Now, what does that have to do with reducing the order of a system? This is the interesting part. So you know that when you have a system, there are some inputs, there are some outputs in general, and inside the system there are these hidden dynamics or states of the system. Good? Now the thing is, not all of these states are easy to control and are easy to observe at the same time. Some states are relatively easy to control, relatively easy to observe, and kind of the same, to the same ease, okay? Some states, it's quite a bit easy to control them, but it's not necessarily easy to observe them, okay? So not all states are the same in terms of being controllable and observable. Some states are kind of equal ease for both of them. Some are one quite a bit dominant compared to the other one. Now, we say that the states in a system that have equal controllability and observability are the ones that properly transfer the energy from input to the output, and those are the important states of the system. Okay? Because if we go back and look at this one more time, some energy of this input is transferred to this output through this mechanism, through the state xi. Some other portion of this energy is transferred through input to output through what? Through this other state of the system, right? For instance, if you consider a mass spring system, right? Let's look at it. So the output here is X, and the input here is, let's say, this force F. And the states of this system, as you know, are X and X dot. And this is the same as Y, this F is the same as U. Good? So when the energy wants to go from this external force to the output of the system, some of it is transferred through X, some of it is transferred through X dot. Why? Because X is related to the energy in the spring, 1/2 kx squared, and X dot is related to the kinetic energy, 1/2 mx dot squared. So some of that energy becomes kinetic energy, some of it becomes potential energy, and this is how this energy from input goes to the output. So each state has a role in transferring some portion of the energy from input to the output. Now, if it is easy for the input to excite that state, to pass the energy to it, and it is easy from that state to pass the energy to the output, you see, these are like two bridges, two nice bridges that this energy can flow from input to the output. But on the other hand, if a state, it's very easy to absorb the energy from the input, it very easily absorbs the energy and changes, but it very hardly gives that energy back to the output. It doesn't like to easily get it back to the output. It's not observable in the output. Then this is like a good bridge, but this is like a bad one. So you get it half of the way in, but the other half you cannot pass the energy. So that's why we say the states that are important in the system are the ones that can easily facilitate the passage of energy from input to the output. And for that to happen, you need an equal or very similar controllability and what? Observability. Okay? That is what we call a balance. The states that have a balance kind of behavior. Those are the ones that we want to keep. The ones that are weak are typically the one that we can ignore and they don't affect the dynamics of the system big time. So how do we balance this controllability and observability? This is how you do it. So you transform your states from X to Z by the transformation matrix T. If you do that, your observability Gramian becomes this. This is the transform version of it. And your controllability Gramian becomes this. Now, we say if these two transformed Gramians can be set equal, and since we transform them, if they can be both equal to the same diagonal matrix like sigma, guess what? This is when the system has balance. These two are equal. And because we transform them, we can transform them to a diagonal format, right? Remember, if you watch my videos on canonical forms, you know one of the major canonical forms is if you can put it in diagonal form, right? So if you can put the system in diagonal form, this T is that transformation matrix, then you can transform both of them to a diagonal form, the same diagonal matrix, and balance the two. Say these two are the same, basically E's. For controllability and observability, guess what? Now we say this should give us those good modes of the system, those important modes of the system. How? First of all, this sigma matrix, this diagonal matrix that both of these will be equal to, it has some singular values. These singular values of this diagonal matrix are called Hankle singular values. Now, why are we talking about singular values, not eigenvalues? The reason is this sigma matrix does not have to be a square matrix. It could be a rectangular matrix like this, n by m. In that case, this matrix has singular values and not eigenvalues. Those sigma values, again, we call them Hankle singular values. How can you find them? The easiest way to do it is this. Because this is not easy to do, the easier way to do it is this. I multiply the original WC and WO together. That will give me a square matrix. I find the eigenvalues of that square matrix. and then I take the square root of those eigenvalues, and those are going to be the Hankle singular values of my system. Okay? Per each state, there will be a corresponding singular value, and that is exactly what you saw over here. Look. Where is it? Let's see if I can find it. There we go. Each state has a corresponding singular value. Now in this system, A was 48 by 48, so you had 48 singular values. Good. Now what? Now, the states have large sigmas, are the ones that are both easy to control and observe. Those are my important dynamics. The ones have smaller sigma are the ones that are hard to excite and detect. Those are the negligible dynamics. So I can get rid of some of the ones with small sigmas and keep the ones with bigger sigmas. And again, look here, we sort them from the highest to the lowest. And it's always good to keep the ones on the left and get rid of the ones on the right. So if I say order is 20, means I keep all of the ones from 1 to 20, and then from 21 to 48, I get rid of them because they have what? They have a smaller sigma, right? Now, in general, as I said, if we sort them from sigma 1 to sigma n, where 1 is the biggest, n is the smallest, then if we decide to reduce the order of system by order r, for instance, in this case, r was 20, and original system was 48, so this was reduced to order 20, then I can show that the difference between the transfer function of the original system and the reduced system, the infinity norm difference between them is going to be less than or equal 2 times summation of all of the Hankle singular values that I neglected from r plus 1, so from 21 all this way to, let's say what, 48. All of the sigmas that I neglected, if I sum them up, multiply by 2, this is like the upper bound of the amount of dynamics that I'm neglecting. Okay? So in this case, I can only neglect from this point, this point, this point. But the best way to decide is to look at the behavior of the system, look how different the states of the system are, how different they are behaving, and then based on that, you can decide, right? So here, I see that, for instance, in terms of impulse response, they are very good. In terms of step response, they are very good. In terms of magnitude of frequency response, they are almost perfect. The only thing that I might be concerned is a phase. Other than that, they are doing great. So this is the essence of Hankle singular values, the controllability and observability Gramians, and how MATLAB model reducer app can help you get rid of a bunch of dynamics that are not super important. Now, one last thing before I finish the video is, you said that you did this simplification 2 different ways. You did it either with Hankle singular values or with pole zero cancellation. And you said that the ones that in Hankle singular values, you got rid of them were the ones with the small sigma. The ones that you got rid of in pole zero cancellation were the ones that had pole and zero close to each other. Can I say that the modes that have pole and zero close to each other are the same as the modes with small sigma? The answer is not necessarily always, but most of the time, yes. Most of the time, the states, the dynamic modes that have close poles and zeros, if they belong to the same thing, then most of the time those in this Hankle singular value are going to be on the right side. Most of the times, not always, okay? And I don't want to get into the condition that under what condition they are not, because again, that opens another can of worm, and I want to keep this video below 50 minutes. So thank you so much for your attention. Hopefully you learned how this tool works in MATLAB and you learn behind the scene what's going on, and I'll see you in the next video. Thank you.